Every galaxy we see is moving away, and that movement is speeding up. That acceleration, it breaks the laws of physics we rely on. We call that mystery dark energy. For more than 100 years, we've charted the universe using Einstein's equations. We thought we knew the rules, but the universe is expanding faster than the rules allow. It shows a hole in our plan for how things work. There's evidence for this problem, and there are new ideas that could change the rules completely. Two precise ways to measure the universe's expansion, they give different answers. They disagree, and there's this energy, a ghostly energy, filling empty space. It has implications for how everything ends. The sky above Mount Wilson was completely black. Just points of light. In the 1920s, Edwin Hubble was there. He used the most powerful telescope in the world. He looked at these faint, fuzzy patches. They called them nebulae. Most thought they were just clouds of gas inside our own galaxy, but Hubble looked closer, and he saw they weren't clouds. They were galaxies, entire islands of stars, each one its own universe, far beyond us, that changed everything. It meant the cosmos was huge. Our galaxy was just one. But then he went further. He measured the light from these galaxies and he saw a shift. The light was stretched toward the red, a redshift. That shift meant something was moving away. The source was receding and the pattern was clear. The farther the galaxy, the bigger the redshift. The bigger the redshift, the faster it was moving away. It was a direct relationship, a clean law, Hubble's law, and the meaning was profound. The universe wasn't static. It wasn't unchanging, it was expanding. Every galaxy moving away from every other. Like space itself was stretching. That was the first real evidence. Evidence the universe had a history, that it started dense and hot. It was the groundwork for the Big Bang. His method was simple, really. He used special stars, Cepheid variables. They pulse in a predictable way. They're like lighthouses. By seeing how dim they looked from here, knowing how bright they actually were, he could figure the distance. They were his standard candles. They let him map the depths. Confirm the distances. His work set the stage. It changed our view from a single Milky Way to an expanding ocean of galaxies, a grand outward flow. It was the universe's first confession. It told us it had a past, that it was changing, but that revelation was just the start. It raised a new question. If everything is flying apart, what started it? What controls the speed? The answer would be stranger than anything they imagined at Mount Wilson. Gravity was the next step. Hubble had seen the universe expanding, but physics has this rule. What goes up comes down. You throw a ball up, Earth's gravity pulls it back, slows it, stops it, brings it down. The whole cosmos has that same gravity, all those galaxies, all that matter. That force, the one that holds you here, should be acting as a brake. After the Big Bang, every galaxy should feel the pull of all the others, a kind of drag, slowing the expansion over billions of years. And this wasn't just an idea. It was in the equations, Einstein's general relativity, Friedman's work. They gave a precise framework. The fate of the universe came down to a balance. How much stuff was in it? The density of all matter and energy, enough stuff, gravity wins, expansion slows, stops, reverses. A big crunch, everything collapsing back. Not enough stuff, it expands forever, but still slowing, like a car coasting on a flat road that never ends. For decades, that was the central question. Which one? The search was for the missing mass, the extra gravity to decide it. Astronomers mapped galaxies, calculated their pull. They planned big projects to measure the deceleration directly. Their tool was a special kind of star explosion, a Type 1, a supernova. It burns with a known brightness. Find these in very distant galaxies, they become perfect mile markers. See how dim they look. You can measure vast distances across time. Compare those distances to the galaxy's redshifts. You can chart how the expansion rate changed over history. The goal was to measure the break, to quantify the slowdown everyone expected. The stage was set to confirm gravity's rule, but the universe had a different plan. The data came in quietly, from telescopes around the world. It was the late 90s. Two teams were working separately on the same question: the Supernova Cosmology project and the High Z supernova search. They were looking for a specific kind of stellar explosion, a Type 1, a supernova. These aren't random. They happen when a white dwarf star pulls too much material from a partner star. It crosses a line and it detonates with a predictable, brilliant flash. That predictability is what makes them useful. They're like cosmic lighthouses. You know their true brightness. So when you see one in a distant galaxy, you measure how dim it looks from here. That dimness tells you the distance. It's a direct measure, across billions of light years. The teams were using these flashes to map the universe's history. They wanted to see how much the expansion had slowed down. They looked deep into the past, capturing light from supernova that exploded when the universe was half its age. They compared the distances they measured to the redshifts of the galaxies. The expectation was a clear curve, a graph showing the slowdown. The data points began to form a line on their screens, and it was the wrong line. The supernova were too faint. They were farther away than any model of a slowing expansion could allow. The only way it made sense was if the universe wasn't slowing down, it was speeding up. In the past, expansion was slower. Today it's faster. Something was pushing it. The teams were stunned. They assumed it was a mistake. Maybe interstellar dust was dimming the light. Maybe the supernova themselves were different. Billions of years ago, they spent months checking, ruling out every possible error. The result held. It was real. The universe's expansion was accelerating. The announcement in 1998 sent a shock through physics. It was a paradigm shift. The force they expected, gravity's pull, was being overpowered by something else. Something invisible in the fabric of space itself. They called it dark energy. This discovery earned the team leaders the Nobel Prize in 2011. It was a measurement that changed the ledger. We now know roughly 70% of everything is this dark energy. It's not matter, it's a property of space, a kind of anti-gravity stretching the cosmos apart. For the first time, we had direct evidence that our fundamental understanding was incomplete. The Rulebook needed a new chapter. They called it dark energy. That's the name for whatever is pushing the cosmos apart. But it's not really a substance, it's more like a property, an energy that's part of empty space itself. Smooth, uniform, the same everywhere, and it has this trait: negative pressure. That's the key. Normal matter has positive pressure. Gravity pulls things together. But dark energy's negative pressure, it's like a tension in space. It makes space stretch. It creates a repulsion. And on the largest scales, that repulsion overcomes gravity. It becomes a kind of cosmic anti-gravity. The simplest form for this energy is something Einstein came up with. He was working on general relativity. The belief then was that the universe was static. But his equations, they kept saying the universe would either collapse or expand. So he added a factor. A fudge factor. He called it the cosmological constant. It was a repulsive force to balance gravity, to hold the universe in a perfect, frozen state. Then Hubble found the expansion. The universe wasn't static. Einstein called the cosmological constant his greatest blunder. He took it out of his equations. But the irony is, that term he threw away is now the leading candidate for dark energy. It represents a constant energy density of the vacuum. As space expands, more space appears. And with it, more of this intrinsic energy. Matter thins out as the universe grows. But this vacuum energy, its density stays the same. That's why it dominates now. For billions of years after the Big Bang, the universe was dense. Matter and radiation controlled the expansion. Gravity was slowing it down. But as everything expanded and diluted, the constant push of the vacuum energy started to win. It took over about 5 billion years ago, and the acceleration began. This model, the cosmological constant, fits the data remarkably well. It's simple. It works, but it creates a problem. A huge problem. When we try to calculate the value of this vacuum energy using quantum field theory, we get a number. And that number is wrong. Not just a little wrong. It's off by a factor of 1 with 120 zeros after it. It's the worst prediction in science. That's the cosmological constant problem. Our two best theories, one for the very large, one for the very small, give answers for the same thing that are unimaginably different. It's a signal, a screaming signal that we're missing something fundamental. So dark energy, in the form of Einstein's constant, explains the acceleration we see. But its origin, that's still a profound mystery. It's the dominant thing in our universe, and we don't know what it truly is. And this suspect, it might not even be acting alone. There's another crack in the model, a number. One number that tells you how fast the universe is expanding right now. The Hubble constant. It's like a speedometer. For every megaparsec of space, that's about 3.25 million light years. It tells you how many extra kilometers per second a galaxy is moving away. Get that number right, and you know the universe's age, its size, its fate. For decades, astronomers have refined it. They have two brilliant ways to measure it. The first looks back to the very beginning, to the afterglow of the Big Bang, the cosmic microwave background. That faint light, captured by satellites like Planck, is a snapshot. The universe at 380,000 years old. By analyzing the tiny temperature ripples in that ancient light, scientists can deduce the ingredients. The amounts of ordinary matter, dark energy. They take those numbers, plug them into the standard model of cosmology, and run the clock forward. 13.8 billion years. That model predicts what the expansion rate should be today. It's an indirect calculation from the baby picture of the universe. The second method is local, direct. It's the modern version of what Edwin Hubble did. Astronomers use tools like the Hubble Space Telescope. They look at stars in our neighborhood. They find Cepheid variables, stars that pulse predictably, which gives away their true brightness. They use those to calibrate distances to nearby galaxies. Then in those galaxies, they find even brighter mile markers. Type 1 a supernova, to reach out farther. By measuring both the distance and the redshift of these galaxies, they get a direct, present-day measurement of the expansion. No model extrapolation, just a direct reading of the cosmic speedometer. Both methods are monuments to human ingenuity. Both are incredibly precise, and they disagree. The Planck measurement from the early universe suggests a slower expansion, more sedate. The local measurements from supernova and Cepheids insist on a faster one. More urgent, the gap isn't a tiny blip. It's a significant difference, about 5 to 10%. That might not sound like much, but in precision cosmology, where measurements are exquisitely fine, it's a yawning chasm. The discrepancy is far larger than the estimated margin of error for either technique. This is the Hubble tension. For years, scientists hoped it was a mistake. Maybe a hidden error in measuring the Cepheid distances. Maybe a subtle flaw in our understanding of the cosmic microwave background. But as the data improved, the tension didn't ease. It hardened, it persisted. That tells us something. It's likely not a measurement error. It's likely a clue. The universe is giving two different answers to the same question. The early universe, seen in the microwave background, tells one story. The modern universe, seen in nearby galaxies, tells another. This tension suggests the standard model, the model we use to connect that ancient past to the present day. The model that's been so successful might be missing a piece. Maybe dark energy isn't a simple constant. Maybe it changes over time. Maybe there was an exotic form of radiation or matter in the early cosmos that tweaked the initial conditions. Or maybe our understanding of gravity itself needs a subtle adjustment. On the largest scales, the Hubble tension is more than a technical disagreement. It's a direct challenge, the universe presenting a puzzle where our two most trusted tools give conflicting instructions. And in that conflict lies the potential for a revolution. A sign that our cosmic rulebook is not yet complete. We're left with this puzzle, The cosmological constant, it's problematic, but we still use it. The reason is pragmatic. It fits the data, but the problems it creates are immense. So physicists have spent decades looking at alternatives, a whole range of them, different paths through the same cosmic maze. One leading contender is quintessence. Think of the cosmological constant as part of the stage, a permanent feature of space itself. Quintessence is more like an actor on that stage. It's a dynamic field, a kind of cosmic fluid filling the universe, and unlike the constant, it can change over time. Its density, its pressure, its influence, all of that can evolve. That offers an elegant explanation for a key observation. Why did dark energy only take over the expansion about 5 billion years ago? If it were just a simple constant, its repulsive effect was always there. But for most of cosmic history, the universe was dense with matter. Gravity's pull was stronger. Only as matter diluted did the constant's push finally win out. Quintessence tells a different story. Maybe this field was weak in the early universe. Maybe it was even attractive, sleeping quietly. Then, as the cosmos changed, the field woke up. Its properties shifted. It began to push. That dynamic nature could solve the calculation problem. The field's energy could naturally settle to the tiny value we see today, instead of the monstrous prediction from quantum theory. But quintessence is elusive. To confirm it, we'd need to detect its subtle evolution, a sign that dark energy's strength isn't constant after all. So far, our best measurements haven't caught it changing. Then there's a more radical path. What if we don't need dark energy at all? What if, instead of inventing a new component for the universe, we've simply misunderstood the oldest force? Gravity. This is the realm of modified gravity. In these theories, Einstein's general relativity, while spectacularly successful, might be an approximation. It might need a tweak on the largest scales, the scale of the entire observable universe. One class of these ideas goes by names like F of R gravity. The R stands for curvature, the fabric of spacetime itself. The theory suggests the relationship between matter and the curvature it creates is more complex than Einstein proposed. On the scale of solar systems or galaxies, it looks exactly the same. But on cosmic scales, this modified relationship could produce an extra repulsive effect, mimicking dark energy without any mysterious energy field. It's not that space is pushing itself apart. It's that our understanding of how gravity works across vast voids is subtly incomplete. Other ideas come from string theory, suggesting our three-dimensional universe might be a membrane, a brain, floating in a higher dimensional space. In that scenario, gravity could leak into the extra dimensions, making it appear weaker on large scales in our world, which could again mimic an accelerating expansion. These are fascinating concepts, mind-bending. They tie the fate of the cosmos to the geometry of hidden realms, and each alternative makes specific predictions. Quintessence predicts a slowly changing expansion rate, something future telescopes could detect. Modified gravity theories often predict different behaviors for how galaxies cluster together under their own weight. Scientists test these predictions against a flood of data, from supernova, the cosmic microwave background, the large-scale structure of the universe. And here's the rub. So far, the simplest model, Einstein's cosmological constant, paired with dark matter, still matches the observations best. It's the baseline. These other ideas aren't ruled out, but they haven't provided a clearer, more compelling fit either. This vibrant competition of ideas, it's not a sign of failure. It's the engine of science, the profound discomfort with the cosmological constant, its gigantic theoretical problem, the persistent Hubble tension. That's what drives physicists to imagine wilder solutions, more beautiful ones. The mystery of the accelerating universe isn't just a question about galaxies moving apart. It's an invitation to rewrite the rules of reality, to look deeper into the fabric of space and time, and to question whether our most trusted equations are telling us the whole story. Dark energy has this push, this cosmic acceleration. But it's not acting alone, there's a counterweight, dark matter. Dark matter is the anchor, it's the gravitational skeleton, it makes up about a quarter of everything. And it holds galaxies together. It sculpts the whole cosmic web. Without that pull, galaxies like ours wouldn't have formed. Stars would have just flown apart. So dark matter is the counterbalance to dark energy's repulsion. That balance is key. It's how you read the universe's history. We can't see dark matter. It doesn't emit light, doesn't absorb it, doesn't reflect it. It's completely transparent, but we know it's there because of gravity. Take a spinning galaxy. The stars on the outer edges orbit at tremendous speeds. All the visible matter, the stars, the gas, it shouldn't be enough gravity to hold them. The rotation curves, the graphs of speed versus distance, they're flat. They should be falling. The only explanation is a massive halo, an unseen mass enveloping the galaxy, holding it together. Then there's gravitational lensing. Massive objects warp space-time. They bend light. When we look at huge galaxy clusters, we see distorted images of galaxies behind them. The bending is immense. Far more than the visible mass can account for. So there has to be an enormous reservoir of invisible mass, dark matter, providing the extra gravity to twist the light. So the universe is filled with these two dominant, invisible things: dark matter, which clumps and pulls, and dark energy, which is smooth and pushes. Our best model for all of this is called Lambda CDM. Lambda, the cosmological constant, for dark energy, CDM for cold dark matter. This model is the foundation. You take the measured amounts of ordinary matter, dark energy. You run the cosmic film forward from the Big Bang, and it predicts the large-scale structure. The patterns in the cosmic microwave background, the existence of galaxy clusters. It's a masterpiece of synthesis, but within it, there's a critical interplay. The amount of dark matter, its behavior, it directly shapes the expansion history. Imagine a universe with more dark matter. The stronger gravitational pull would have braked the expansion more aggressively in the past. The transition to acceleration would have happened later. Maybe not at all. Less dark matter, and dark energy would have dominated sooner. Our precise measurements of the cosmic microwave background, they're essentially a precise measurement of the dark matter content of the young universe. That measurement feeds into our prediction for how fast the universe should be expanding today. A prediction that's now in tension with direct local measurements. That tension is fueling new ideas. Maybe dark matter and dark energy aren't completely separate. Could they interact? Some theories suggest dark matter might slowly decay into dark energy, changing the balance over time. Others propose multiple types of dark matter, some that clump strongly, some that behave more like a smooth, warm fluid. These variations could subtly alter the expansion history, potentially bridging the gap between the early universe's story and the modern one. The fate of everything is in this invisible dance. Dark matter's gravity pulls the cosmos back together. Dark energy's repulsion drives it eternally apart. Which force wins depends on their precise natures. Natures we're still struggling to define. By studying the effects of dark matter on galaxy shapes, on the bending of light, we're not just solving one mystery. We're gathering clues to the other. They're two sides of the same cosmic coin. Unraveling one might finally illuminate the other, and reveal the true story of where all this is headed. The story of expansion starts before galaxies, before anything really. It goes back to the very first instant. To understand the acceleration we see now, you have to look back there. To the beginning, to something called cosmic inflation. So picture the universe, smaller than an atom, dense, hot, and in that moment, a theory says, a strange energy field took over. It had this property. It created a repulsive gravity, and it triggered an expansion, an exponential one. Space itself stretched, faster than light. In less than a blink, the universe grew by a factor of 10 to the 26th, from subatomic to cosmic size. Then, just as fast as it started, that inflationary field decayed. it transformed. Its energy became the hot soup of particles, the radiation that powered the Big Bang. Inflation solves puzzles. It explains why the cosmic microwave background is so uniform. Opposite sides of the sky have the same temperature because they were once close together, before inflation stretched them apart, and it explains why space looks flat. Inflation smoothed it out, stretched it, like blowing up a balloon to an enormous size. Now there's a parallel here. Inflation was driven by a repulsive energy. Dark energy driving today's acceleration is also a repulsive energy. So you have to ask, are they related? Some scientists wonder. Maybe dark energy is a faint echo, a remnant of that first field that never fully went away, or maybe a reactivation. A late-time inflation, but much gentler, much slower, but the comparison shows a difference. A stark one. The inflationary field was powerful, immensely powerful. Its energy density was colossal. Dark energy, by contrast, is weak, incredibly weak. Its density is about 120 orders of magnitude smaller. That's not a small difference. It's the largest discrepancy in all of physics. Observations help separate them. The patterns in the cosmic microwave background, those are from inflation. They tell us about that early burst, the distribution of galaxies today, that tells us about dark energy's modern influence. And the data suggests they're distinct, different phenomena, governed by different rules, yet they share a similarity, a profound one. Both are periods where the universe's expansion is dominated not by matter, but by the inherent energy of space itself. That changes the narrative. It suggests the universe might not have one story of expansion, but multiple chapters. An initial, violent, inflationary chapter. Then a long, slow chapter dominated by matter and gravity. And now, a new, accelerating chapter, driven by dark energy, each epoch governed by a different force. Linking these chapters deepens the mystery. It shows the cosmos has used this trick, this repulsive expansion, more than once. But why? What principle allows space to have these self-reinforcing properties? At different times, with such wildly different strengths. This historical view doesn't solve dark energy. Instead, it frames it within a grander pattern. A more perplexing one. Our physics can describe each chapter's effects, but the underlying script, the reason for these shifting rules, that remains hidden. Written in a language we haven't fully deciphered. The Hubble tension isn't the only one. There's a whole list of these cosmic curiosities now. Little signs that maybe something in our standard picture isn't quite right. These are the observational anomalies, data points that don't fit the smooth curve of our best model. Take the sigma 8 tension. Sigma 8 is a number. It tells you how clumpy the universe is, how much matter has gathered into clusters and filaments. We can predict this number from the cosmic microwave background. That ancient light shows us the initial seeds of structure. You run the model forward, you include dark matter and dark energy, and you get a prediction for how clumpy the universe should be today. But then astronomers go and measure it directly. They survey millions of galaxies. They map their three-dimensional distribution, and they often find a lower value. The universe looks slightly smoother, less clumped together than the model predicts. The discrepancy isn't huge, but it's persistent. It's as if the gravitational glue of dark matter wasn't quite as effective. Like it didn't pull things together over the last 13.8 billion years as strongly as we thought. Maybe dark energy played a more active role. Maybe it suppressed growth. Or maybe dark matter has properties we haven't accounted for. It's a quiet tension. But it's another thread pulling at the fabric of Lambda CDM. Then there's the cold spot. In the cosmic microwave background, it's remarkably uniform, but there's this one region, about 5 degrees across. It's unusually cold. A vast, subtle chill in the afterglow of creation. Statistically, it's an outlier. It could just be a rare fluctuation, random chance in the cosmic lottery. But its size and significance have led to more exotic ideas. Could it be the imprint of a cosmic texture? a defect in the structure of space-time from the early universe. Some have even speculated, cautiously, that it might be evidence of a collision with another universe in the vast multiverse, a bruise on our cosmos from a long-ago encounter with a neighbor we cannot see. These ideas are speculative, but the cold spot remains an unexplained feature, a question mark on the map of the infant cosmos. On even larger scales, astronomers trace the motions of galaxies. They don't just move with the overall expansion, they also stream. They stream toward regions of greater mass, pulled by the gravitational tides of immense superclusters. These are called bulk flows, and some observations suggest these flows might be a little too fast, a little too coherent over vast distances, too fast to be easily explained by the visible distribution of matter. And dark matter, in our standard model, it's as if there's an extra pull, a pull from something beyond our current map, a suggestion of larger structures. Or maybe a modification in how gravity operates over these immense spans. None of these anomalies alone is a smoking gun. Each one could, with enough statistical gymnastics, be folded into the standard model. Called a fluke or a measurement challenge, but together they form a pattern, a constellation of small inconsistencies. They are the places where the universe seems to be nudging us, hinting that our beautifully constructed Lambda CDM model, for all its success, it might be a brilliant approximation, an approximation of a deeper, more complex reality. These are not failures of science, they are its engine. Every anomaly is a clue, a signpost pointing toward a potential discovery. They remind us that our physics, as powerful as it is, maps the territory we have explored. The universe is under no obligation to make sense to us. Its job is to exist. Our job is to observe, to question, and to be humble enough to rewrite the rules when the evidence demands it. These curiosities keep the field alive, vibrant, and open to the possibility that the next great breakthrough in understanding the cosmos is hidden right there, in a subtle mismatch between prediction and observation. Empty space isn't empty. That's the first thing you learn from quantum physics. If you could see the universe on the smallest scale, you'd see a chaotic sea. Particles and antiparticles flickering into existence. They borrow energy from the vacuum for an instant, then annihilate and vanish. These are quantum fluctuations. Virtual particles. They come from Heisenberg's uncertainty principle, which says you can't know both the energy of a system and the time you measure it with perfect precision. So on tiny timescales, energy can fluctuate. It can appear as these particle-antiparticle pairs. Every cubic centimeter of vacuum is alive with this. An infinite number of possible vibrations, each adding a tiny bit of energy. That's the zero-point energy of the vacuum. Now, according to Einstein's gravity, general relativity, all energy curves space-time. It has a gravitational effect. So this vacuum energy, this quantum foam, should be curving the cosmos. It should act as a cosmological constant, a repulsive force woven into nothingness itself. So physicists did the math. They added up all the contributions from every quantum field, from every possible particle. The calculation gives a number for the energy density of the vacuum. And that number is monstrous. It's about 1 with 120 zeros after it. 10 to the power of 120. An amount of energy so vast it's meaningless. If this prediction were right, the gravitational repulsion from this vacuum energy would have been unimaginably strong. From the first instant of the Big Bang, the universe would have expanded so violently that no stars could form, no galaxies, no atoms could hold together. The cosmos would have been torn apart in a fraction of a second. A barren, accelerating void. We wouldn't be here to see it, but we are here, and we see a universe with structure, with galaxies, and we measure the actual effect of vacuum energy. We call it dark energy. Its observed value is tiny, unbelievably tiny. The real cosmological constant is about 1/10 of an attojoule per cubic meter. To get from the theoretical prediction to the observed value, You have to divide by 10 to the 120th power. Cancel out 120 orders of magnitude. This isn't a small error. It's the worst prediction in the history of science. This is the vacuum catastrophe, the cosmological constant problem. It's a screaming disconnect between our two most successful theories. Quantum field theory, which governs the very small, and general relativity, which governs the very large. Both are spectacularly accurate in their own domains. But when you try to bring them together to ask what gravity does to the quantum vacuum, they give answers that aren't just different. They're catastrophically, impossibly different. It's like asking two expert watchmakers for the time, and one says midnight while the other says 15 billion years past noon. So what's going on? How do we resolve this? Scientists have proposed pathways. Some look to new physics like supersymmetry, a theoretical idea where every known particle has a superpartner, a heavier twin. In a perfectly supersymmetric world, the positive contributions to vacuum energy from particles and the negative contributions from their superpartners would exactly cancel. The sum would be zero, but we don't live in that perfect world. Supersymmetry, if it exists, is broken. The cancellation would be almost, but not quite, perfect, leaving behind the tiny residue we see as dark energy. It's an elegant idea, but so far, particle colliders have found no evidence for these superpartners. Then there's a more philosophical approach, the Anthropic principle. It starts with the idea of a multiverse, a vast, maybe infinite, collection of universes, each with different physical constants, different values for the vacuum energy. In most of these universes, the cosmological constant is enormous. Those universes are sterile, empty. But in a very, very rare subset, by sheer chance, the constant is tiny, small enough for galaxies to form, for stars to ignite, for life to emerge. We, of course, find ourselves in one of those rare, habitable universes. Our existence selects for the value we measure. This isn't so much an explanation as a context. It moves the question from why is the constant so small, to why are we in a universe where it is small. For some, this is a profound insight into our place in reality. For others, it feels like a surrender, an untestable retreat from a physical explanation. The vacuum catastrophe is more than a numerical puzzle. It's a direct challenge to our understanding of nothingness. We thought empty space was simple, inert, a passive stage, but quantum physics says it's dynamic, a vibrant, energetic field. And cosmology tells us that this energy, or something eerily like it, is shaping the fate of everything. Reconciling these views isn't optional. It's essential. Many believe the answer lies in a theory of quantum gravity, a framework that blends the quantum world with the geometry of space-time. String theory, or loop quantum gravity, or something yet unnamed. These are the realms where the true nature of the vacuum might be understood, where the infinite sums of quantum field theory might be tamed by the very structure of space itself. So the mystery of the accelerating expansion leads us here, to a fundamental rift in physics. It suggests that dark energy isn't just a curious component of our universe. It's a signpost, pointing toward a deeper layer of reality, a layer where our concepts of something and nothing, of emptiness and energy, are waiting to be rewritten. There's this number. It's called the equation of state. For dark energy, it's just the ratio between its pressure and its density. We label it W. If dark energy is Einstein's cosmological constant, if it's truly constant, then W equals exactly -1. That value locks in a future of smooth, relentless acceleration. But if that number is different even slightly, if it drifts over time, then the ultimate destiny of everything changes. So take the path where W equals -1. Acceleration continues. In about 100 billion years, every galaxy not already bound to our local group gets pushed beyond our cosmic horizon. Their light stretches to wavelengths longer than the observable universe itself, and it just fades from view. The sky goes dark. No more distant galaxies. just a handful of nearby stars in one merged, aging galaxy. Star formation has long since stopped. The gas for new stars is locked away in dead stellar remnants. Over trillions of years, the last stars burn out. Planets go cold. Even the protons in atoms may decay. That's a hypothesis in particle physics. The universe becomes a vast, expanding sea of incredibly diluted particles and radiation, all drifting farther apart. Temperatures approach absolute zero. That's the big freeze, heat death, not an explosion, a slow, quiet fade into darkness and cold. It's the most likely outcome based on our best measurements right now. But there's a more violent alternative. What if dark energy isn't constant? What if it's something like quintessence and its strength grows? In that scenario, W could be less than -1. The repulsive pressure gets more intense as the universe expands. Acceleration doesn't just continue, it runs away. In that future, the repulsive force of dark energy would eventually overcome every binding force. Starting with the largest, first, it tears apart galaxy clusters, then individual galaxies. The gravitational hold of a galaxy's central black hole becomes insufficient. Stars get flung apart. As the runaway acceleration intensifies, it overcomes the gravity holding solar systems together. Planets are ripped from their stars. Then the electromagnetic forces holding matter together fail. In the final moments, atoms themselves are torn apart, nuclei shredded. The fabric of spacetime might be disrupted. That's the Big Rip. A catastrophic end where expansion becomes so violently fast it disintegrates all structure. The timescale depends on how much W deviates from -1. It could be tens of billions of years from now or far longer, but the outcome is total. There are gentler possibilities. Maybe dark energy decays away. Its influence weakens and vanishes, letting gravity reassert dominance. The universe's expansion would slow again, potentially leading to a distant Big Crunch, a collapse back into a hot, dense state. Or maybe our understanding of gravity is wrong. Maybe on the largest scales, a correction to Einstein's equations emerges that makes dark energy unnecessary, pointing to a completely different future we can't yet see. Our ability to forecast which fate awaits us depends entirely on solving the puzzle we face today. By measuring the expansion history with exquisite precision, astronomers are trying to pin down that crucial number W and see if it changes. Projects like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope are designed to map billions of galaxies and thousands of supernova. They'll measure the subtle tug-of-war between dark energy's push and gravity's pull across cosmic history. They're taking the universe's blood pressure, looking for any sign its cosmic heartbeat is changing rhythm. That transforms the mystery from an abstract curiosity into an existential investigation. The forces that will determine whether the cosmos ends in ice or fire or disintegration. They're hidden within the enigma of today's acceleration. Understanding why the universe is expanding faster than physics can explain isn't just about fixing our models of the past. It's about reading the final chapter of the story of everything. And that realization lends a profound urgency to the search. It connects the fate of distant, cold galaxies trillions of years from now to the precise measurements we're making in our own fleeting moment of cosmic light. The search isn't just theory anymore. It's a technology race. To really know dark energy, you need a new kind of sight. A deeper, wider, more precise map of the cosmos than we've ever had. And that map is being drawn now by a new generation of telescopes. On the ground and in space. Up in the Chilean Andes, construction is finished on the Vera C. Rubin Observatory. Its mission is simple and huge. Over 10 years, it will scan the whole southern sky every few nights. It won't study a few objects. It will catalog billions, galaxies, stars, supernova. It will make a cosmic movie, a time-lapse of the universe. That relentless survey will find millions of Type 1 a supernova, those key distance markers, building a statistical picture of expansion so strong it drowns out random errors. But its main power is in a subtle effect. Weak gravitational lensing, light from distant galaxies comes to us and it passes through the cosmic web. Dark matter, clusters of galaxies. That mass warps space-time, very slightly distorting the shapes of those background galaxies. By measuring the subtle, statistical warping of billions of galaxy shapes, Rubin can trace the invisible scaffolding of dark matter. And by seeing how that scaffolding grows and changes over cosmic time, scientists can measure the competing pulls, dark matter's gravity against dark energy's repulsion. With stunning accuracy. Meanwhile, in space, there's the recently launched Euclid mission and the forthcoming Nancy Grace Roman Space Telescope. They take a complementary approach. Euclid is a European Space Agency mission. It's already capturing razor-sharp images and spectra over a huge part of the sky. Roman, named for Nas, a first chief astronomer, will have a field of view 100 times larger than Hubble's. These observatories are good at another technique. Measuring Baryon acoustic oscillations, it's a mouthful. It refers to a fossilized imprint from the early universe. In the hot plasma of the first few 100,000 years, pressure waves, sound waves, rippled through the cosmic fluid. When the universe cooled enough for atoms to form, those waves froze in place. The result is a preferred scale, a standard ruler etched into the distribution of galaxies. By measuring this ruler at different times in cosmic history, astronomers can track how the expansion of space has stretched it over time. It's like finding a rubber ruler in the ancient universe and seeing how much it has stretched by today. That gives a direct, clean measurement of expansion history. Independent of supernova, on the ground there's the Dark Energy Spectroscopic Instrument, DESI. It's already at work, mounted on a telescope in Arizona. It's not taking pretty pictures, it's collecting spectra. The light of millions of galaxies is split into rainbows, revealing their precise redshifts. This lets DESI build a three-dimensional map of the universe, plotting galaxies not just by their position on the sky, but by their distance from us. That immense 3D chart shows the cosmic web in breathtaking detail. The vast filaments of galaxies and the huge voids between them. The growth of this web over time is exquisitely sensitive to the influence of dark energy. By comparing the map to theoretical predictions, DESI can constrain the properties of dark energy with a precision of a fraction of a percent. These aren't isolated projects. They are parts of a global, collaborative strategy. Each technique, supernova, weak lensing, Baryon acoustic oscillations, has its own strengths and potential blind spots. By combining them, scientists can cross-check results, cancel out systematic errors, build an irrefutable case. The goal is to tighten the constraints on that crucial number. The equation of state of dark energy, to see if it truly is a constant negative one or if it wavers. They aim to resolve the Hubble tension by providing an overwhelming tide of data, revealing whether the discrepancy is a measurement glitch or a fundamental flaw in our model. The engineering behind these efforts is itself a marvel. The Rubin Observatory's camera is the largest digital camera ever built for astronomy. Roman and Euclid need optics of flawless precision for their wide-field measurements. DESI uses 5,000 robotically controlled fibers to capture the light of individual galaxies, night after night. This is big science, a testament to human curiosity and cooperation. Over the next decade, as this data deluge begins, we stand on the threshold. These instruments may finally give the clarity needed to choose between our competing theories. They might confirm the simple, puzzling cosmological constant. They might catch dark energy in the act of changing, pointing to dynamic quintessence. Or they might reveal something entirely unexpected, a new anomaly that opens a door we didn't even know was there. The mystery of the accelerating universe is being pursued with the most powerful tools we've ever built. And the answer is written in the light of billions of ancient galaxies, finally coming into focus. This pushes us towards something almost philosophical. If the vacuum energy is so finely tuned, so perfectly suited for our existence, Maybe that tuning isn't a coincidence. Maybe it's a selection effect. That's where the idea of the multiverse comes in. It's a radical concept, that our universe with all its billions of galaxies is just one bubble, one island in a vast cosmic archipelago. Each with its own physical laws, each with its own constants. Think of it like a cosmic lottery. In that picture, the vacuum energy isn't dictated by one fundamental equation. It's a random draw. Some universes have a huge positive cosmological constant. They expand so violently nothing ever forms. Others have a large negative value and they collapse instantly. And in a vanishingly rare few, by sheer chance, the number lands in that tiny, habitable range, where galaxies can coalesce, stars can burn, and life can ask questions. We, of course, find ourselves in one of those rare universes. Our very existence filters the reality we see. That's the anthropic principle in its strongest form. It doesn't explain why the constant has its value. It explains why we observe that value. But how could a multiverse physically exist? The leading candidate comes from a tweak to cosmic inflation. That initial explosive expansion of the early universe. In the theory of eternal inflation, once inflation starts, it never completely stops. It's like a pot of water boiling forever. Our entire observable universe is one bubble that formed when inflation ended in our local region. But beyond our bubble, the inflationary field continues, spawning new bubbles endlessly. Each new bubble universe cools and develops with its own random set of physical parameters. A different vacuum energy in each one. String theory provides another landscape. The attempt to unify all forces. It suggests there might be an astronomical number of possible stable configurations for the extra dimensions it proposes. Each configuration corresponds to a different universe with different physics. Our universe's specific, tiny dark energy value is just one point in a vast landscape of possibilities. This idea elegantly sidesteps the vacuum catastrophe. That monstrous calculation from quantum field theory isn't wrong. That huge energy density probably does exist somewhere. But in the multiverse, all possible values exist somewhere. We simply live where the number is small enough for us to be here to measure it. The problem of fine-tuning dissolves into a matter of statistics. In an infinite ensemble, yet this comes at a cost. The multiverse is controversial. Its greatest challenge is testability. If these other universes are causally disconnected from us, forever beyond our horizon, can we ever gather evidence? Some physicists argue this moves the idea from science into metaphysics. Untestable speculation. Proponents counter that we might find indirect signatures. Perhaps a collision with another bubble universe left an imprint on the cosmic microwave background, like the cold spot we discussed. Or maybe the statistical predictions of the multiverse could one day be matched against the distribution of vacuum energies, if we could somehow infer them. For now, it remains a compelling framework, not a confirmed theory. The philosophical implications are profound. It suggests our universe's accelerating expansion, and all its finely tuned constants, might not have a unique, elegant explanation. There may be no single, beautiful equation that predicts the value of dark energy. Instead, it could be a cosmic accident, a random ticket in a lottery of unimaginable scale. This can feel like a Copernican demotion. Our universe isn't central or special or uniquely designed. It's just one among countless others, most of which are barren and empty. But it also expands the mystery in a breathtaking way. The answer to why our universe is the way it is may not lie within it. The solution might exist in a reality so vast that our entire cosmos is just a single data point. It invites us to consider that the true nature of existence encompasses realities beyond our imagination, where every possible physical law plays out. The search for why our universe accelerates becomes a search for our address. In a much grander and more mysterious meta-cosmos, this mystery of acceleration. It puts us in a long tradition of cosmic humility. For centuries we thought Earth was the still center. The stars were fixed on a crystal sphere. That model was intuitive. It matched what we saw, but it was wrong. Moving to a sun-centered system was a shock. It removed us from a privileged place. Later, we thought the Milky Way was the whole universe. Then Edwin Hubble showed it was just one island, among countless others. Each revolution expanded the scale of reality and shrank our significance. Each time, we had to rewrite the textbooks. This discovery of an accelerating universe, driven by a force we can't see, can't yet fully define, it's the latest chapter in that story, a direct message from nature. That our current rulebook, however successful, is provisional. Our physics can send probes to other worlds, can peer back to the first moments of time. And yet it's meta-phenomenon it can't yet contain, within its equations. This isn't a failure. It's the essential process of science. The universe is under no obligation to conform to our understanding. Its job is to be. Our job is to observe, to question, to adapt. That raises a deep question. Are we, with dark energy and the Hubble tension, approaching a fundamental limit to what we can know? Or is this just another bend in the road? The history of science suggests the latter. Every time we've hit an apparent wall, the ultraviolet catastrophe that led to quantum mechanics, the orbit of Mercury that demanded a new theory of gravity, the wall turned out to be a doorway. The crisis became the catalyst for a leap in understanding. The accelerating universe presents such a crisis. It challenges the dream of a final theory, a single set of equations for all forces for all time. Perhaps the cosmos is inherently too rich, too layered for such a tidy conclusion. Perhaps it will always retain the capacity to surprise us, to force a paradigm shift, just when we think the puzzle is nearly solved. This interplay is the true engine. Observation reveals an anomaly, galaxies moving too fast. Theory scrambles to explain it, proposing dark energy or modified gravity. New observations then test those theories, revealing further tensions, further curiosities. Philosophy steps in to ask what it all means for our place. For the nature of knowledge itself, it's a beautiful, self-correcting cycle. Science, at its best, isn't just a collection of facts. It's a method for cultivating wonder. It's about learning to ask better questions, more profound questions, the question of why the universe accelerates. That question is far more valuable than any premature answer. It keeps the conversation with the cosmos alive and urgent. There's a certain courage required to stand at the edge of the known, looking into a mystery that defies our core theories. It requires the humility to say we do not know, and the optimism to believe we can find out. This pursuit, with all its uncertainty and wonder, it's a defining human endeavor. As we map the cosmos with more powerful tools, we're not just charting galaxies, we're charting the expanding frontiers of our own understanding. The journey itself accelerates, filled with more questions with each answer we find, and in that endless, accelerating quest, we find not frustration, but the deepest source of awe. The recognition that the universe is far stranger, more vast, more magnificent than we ever supposed. Our story within it is still being written, one observation, one question at a time. Neutrinos are these ghostly particles. Billions pass through your thumb every second from the sun, from stars. They almost never interact. They have almost no mass, but they were born in the Big Bang in stellar explosions, and they might hold a small key to how the universe expands. Their collective influence, woven through everything, could tweak the numbers just enough. You have to go back to the first second. The universe was a searing plasma, filled with a dense sea of neutrinos. As everything expanded and cooled, these neutrinos decoupled. They started streaming freely through space. That relic sea is still here. The cosmic neutrino background. It's much colder than the cosmic microwave background, and far harder to detect. But its gravitational effect is real. It adds to the total energy budget of the universe. Not much, a fraction of a percent compared to dark matter or dark energy. But in cosmology, every fraction counts. Their properties are what's interesting. For a long time, we thought neutrinos were massless. But experiments on Earth revealed something. Neutrinos oscillate. An electron neutrino from the Sun can transform into a muon neutrino or a tau neutrino as it travels. That transformation only happens if neutrinos have mass. A tiny, tiny mass, but mass nonetheless. That discovery confirmed the standard model of particle physics was incomplete, and it gave cosmologists a new variable for their models of the early universe. The mass of neutrinos affects how structure forms. In the first few 100,000 years, these lightweight particles were moving nearly at light speed. That high speed meant they could smooth things out. They could stream out of regions of high density, dragging gravitational potential with them. That suppressed the growth of the very smallest clumps of matter. It left an imprint on the large-scale structure we see today. The cosmic microwave background from Planck is sensitive to this. By analyzing those ancient temperature patterns, scientists can place an upper limit on the sum of neutrino masses. The data says the total is very small, but not zero. That constraint is vital. It rules out models where neutrinos make up a large part of dark matter. And it sharpens our picture of the cosmic ingredients. Now, the Hubble tension. Could neutrinos help explain it? Possibly. If their properties are slightly different than we assume, they could have altered the expansion history in a subtle way. Some theories propose sterile neutrinos. These are hypothetical particles that don't even feel the weak nuclear force. They interact only through gravity. If they exist, they could have been a form of warm dark matter in the early universe. That would change how quickly structures formed, and by extension, how we interpret the early universe's clues about today's expansion rate. Others speculate about connections between neutrinos and dark energy. Could a coupling between these ghostly particles and the dark energy field have shifted the balance over time? It's a speculative bridge. The pursuit of these questions is driving new experiments. Huge detectors buried deep underground in old mines under mountains. They wait for the rare flash of light when a neutrino finally interacts. They're hunting for the absolute mass of the neutrino and searching for signs of those sterile cousins. Meanwhile, cosmological surveys are getting so precise they're beginning to feel the gravitational footprint of neutrino mass indirectly, through its subtle suppression of galaxy clustering. This is the convergence in modern cosmology. To solve the mystery of the accelerating universe, we have to listen to the faintest whispers from the smallest things. The journey of a neutrino, from the first instant to a detector under a mile of rock, ties together scales of reality that seem impossibly separate. The universe's expansion isn't just a story of vast, empty spaces and dark energy. It's also written in the properties of the most abundant yet most elusive particles. Solving the puzzle may require us to understand not just the dark components, but the lightest ones we've already found, and how they've been quietly shaping everything from the very beginning. Physics has always assumed the constants of nature are fixed. The speed of light, gravity's strength, the electron's charge. These numbers are the pillars. They're supposed to be unchanging, but what if they aren't? What if, over billions of years, they drift? It's a radical idea. If it's true, it could explain the universe's accelerating expansion without dark energy. Take the gravitational constant, big G. It sets the pull between masses. In Einstein's equations, it's a fixed number. But if gravity weakened over time or across vast distances, the effect would be profound. The braking force on expansion would diminish. Galaxies would seem to fly apart faster than predicted, not because of a repulsive push, but because the pull holding them back is fading. The observed acceleration could be an illusion, a symptom of a constant that isn't constant. Scientists have long tried to test this. One key target is the fine structure constant, alpha. It governs the electromagnetic force. It ties together the speed of light, the electron's charge, and Planck's constant. It determines how atoms hold together. To see if it's changed, astronomers look to the most distant light. Quasars. Their light passes through interstellar gas clouds which absorb specific wavelengths. It creates a barcode pattern in the spectrum. The spacing of those lines depends on the value of alpha. By comparing quasar barcodes to lab ones on Earth, researchers can check if alpha was different when the universe was young. The results are contentious. Some teams report hints of a tiny variation over cosmic time. Others, using different data, find no change at all. The measurements are at the very edge of our capability. Systematic errors are hard to rule out, so the question remains open. A whisper in extremely precise data. Theoretical frameworks allow for this. Scalar tensor theories of gravity introduce an additional field. In these models, the effective strength of gravity can evolve as this cosmic field changes. Another idea is varying speed of light cosmology. It suggests the speed of light could have been much higher early on. These aren't mainstream ideas, but they're serious proposals. They try to solve multiple puzzles at once, including acceleration. Testing them is a monumental challenge. It requires cross-checking observations from wildly different epochs. The light from a quasar, the afterglow of the Big Bang, nuclear reactions in ancient stars, the precise timing of pulsars, all become witnesses to a shifting rulebook. Any claimed variation must be consistent across all these tests, a bar that hasn't been met. The implications are staggering. If a constant like alpha or big G is found to vary, it means our laws of physics aren't universal and eternal. They're local bylaws, specific to our cosmic epoch and corner of space. They could evolve as the universe ages. That turns the search for a final theory on its head. The mystery of acceleration becomes part of a deeper narrative. A story where the fabric of reality is dynamic, learning its own rules as it goes. This line of inquiry stretches the imagination. The answer we seek may not be a new component in the universe. It may be a fundamental rethinking of what a law of nature even is. The oldest light we can see is just a whisper. It fills the whole sky, a faint, cold glow everywhere. That's the cosmic microwave background, the afterglow of the Big Bang from when the universe was 380,000 years old. Before that, it was all hot plasma. A dense fog. Electrons and protons were scattering photons, trapping the light. Then expansion cooled things. Electrons and protons combined into neutral hydrogen. The fog cleared, and the light was suddenly free. That first flash of transparency is what we see now, stretched out over 13.8 billion years of expansion into microwaves. The light isn't perfectly smooth. If you could see it, you'd see tiny temperature variations, ripples, just one part in 100,000. Those ripples are the seeds of everything. The denser, warmer spots became the gravitational wells for galaxies and clusters. The cooler spots became the voids. It's a frozen record, a baby picture with information in its texture. Satellites like WMAP and Planck mapped this pattern. They measured the angular size of the ripples. In the early universe, there were sound waves in the plasma. Baryon acoustic oscillations. They created a preferred scale, a standard ruler, imprinted on the light. By measuring how big that ruler looks on our sky, cosmologists can work backwards. They can deduce the geometry of the universe, whether space is flat or curved. The CMB tells us space is flat on the largest scales. That's a crucial piece. From this flat geometry and the fluctuation pattern, scientists extract the recipe. The amounts of ordinary matter, and dark energy. They also get the expansion rate of the universe back then. The process uses statistics, comparing the observed pattern to millions of simulated universes. The model that fits best is Lambda CDM. It says the universe is about 5% ordinary matter, 27% dark matter, 68% dark energy. This analysis gives a prediction. You take those early ingredients and run the equations of general relativity forward through 13.8 billion years. The model predicts what the expansion rate should be right now. That predicted value is the Hubble constant from the early universe's perspective. It's an indirect derivation, but it's precise. And that's where the tension is. This CMB-derived value for today's rate is consistently lower than the value measured directly in our local universe. Using supernova and Cepheid stars, the early universe's story suggests a slower pace. The local universe says it's faster. That's the Hubble tension. The CMB is its primary anchor. It's not that the CMB measurement is wrong. It's exquisitely precise. It's that the chain of inference from that ancient light to today relies on the standard model being completely correct. If something is missing from the model, an exotic particle, a tweak to gravity, some early dark energy, then the prediction for today's rate would shift. The CMB also constrains ideas about inflation. Certain patterns in the polarization could reveal the energy scale of inflation, maybe linking it to dark energy. And some propose an early dark energy phase that could have changed the sound horizon scale measured in the CMB, which might reconcile the early and late expansion rates. So this ancient glow is a cornerstone and a conundrum. It provides the strongest evidence for our standard model, yet the prediction it makes about our current epoch conflicts with direct observations. It's a guide and a reminder. The universe's first photograph tells a clear story, but when we compare that story to the universe today, the chapters don't line up. Interpreting this light requires assumptions, and those assumptions are now under scrutiny. The CMB isn't just a snapshot of the past. It's a mirror, reflecting the gaps in our understanding of the present. The cosmos has a rhythm, a kind of frozen echo from its very beginning. When everything was that searing plasma, a dense soup of particles and light, it wasn't silent. There were pressure waves, actual sound waves moving through that hot fluid, driven by gravity pulling matter together and radiation pressure pushing it apart. For hundreds of thousands of years, these acoustic oscillations traveled outward, from every slight overdensity, like ripples from a stone dropped in a pond. Then the universe cooled enough for atoms to form, the fog cleared, the light escaped, and the sound waves just froze in place, their progress halted. That frozen wave front left a permanent mark. It created a subtle, spherical shell of matter around those initial seeds, a shell with a very specific radius. That radius is the sound horizon scale, the distance a sound wave could travel from the Big Bang until the moment the universe became transparent, about 500 million light-years across. This scale became a standard ruler, etched into the fabric of the cosmos. Billions of years later, when galaxies formed, they were more likely to form along these fossilized shells. So when we map the positions of millions of galaxies in 3 dimensions, we don't just see a random scatter. We see a subtle statistical preference. A galaxy is more likely to be found about 500 million light-years away from another galaxy than at any other distance. It's a faint signal in a sea of data. But by surveying enough of the sky, it emerges, a cosmic fingerprint. That's the power of Baryon acoustic oscillations. They give us a fixed measuring stick of known length. Imprinted across the entire universe, we can observe this ruler at different epochs by looking at galaxies at different redshifts. When we see it in nearby galaxies, we measure its apparent size now. When we see it in extremely distant galaxies, we're looking back in time, measuring its apparent size then. By comparing these, we can see exactly how much the universe has stretched in the intervening billions of years. It's a direct measurement of expansion history, independent of the brightness of stars or the details of the cosmic microwave background. Projects like the Sloan Digital Sky Survey and now the Dark Energy Spectroscopic Instrument are built for this. They use immense telescopes and spectrographs to collect the light of tens of millions of galaxies, determining their precise distances. They build vast 3-dimensional maps of the cosmos. And within those maps, supercomputers search for that subtle statistical peak, that preferred separation at different slices of cosmic time. The results are profound. Baryon acoustic oscillation measurements strongly support the standard model of cosmology. They confirm the flat geometry of space. They provide an independent measurement of the amounts of dark matter and dark energy. And when used to infer the current expansion rate, they land in an interesting middle ground. Their value for the Hubble constant tends to sit between the higher value from local supernova and the lower value from the cosmic microwave background. It doesn't resolve the tension, but it deepens the plot, showing that the discrepancy isn't just an artifact of one flawed method. This technique has a particular strength. It doesn't rely on understanding the intrinsic brightness of any object. A standard ruler is just a geometric measurement. This avoids many of the systematic errors that can plague supernova studies. Like interstellar dust or evolutionary changes in the stars themselves, it provides a clean, geometric check on the expansion story. So these fossil sound waves, these Baryon acoustic oscillations, are more than a cosmic curiosity. They are a fundamental calibration tool, a ruler built into the universe at its birth. By learning to read its markings across deep time, we gain a direct, robust account of how space has stretched. And that account, when combined with all the others, keeps pointing toward the same unsettling conclusion. Our maps are precise, our measurements are multiple, and they all whisper that a piece of the cosmic puzzle is still missing from our grasp. Between the cosmic web, those bright threads of galaxies, you have the voids. These huge empty spaces, they're not small, they're enormous, hundreds of millions of light years across. Almost no galaxies inside them, just a trace of gas. By volume, they're most of what's out there. And that emptiness, it might be bending how we see the universe expanding. It comes down to gravity, or the lack of it. In a galaxy cluster, all that mass pulls on itself. It holds back the expansion a little, but in a void, there's nothing to pull, nothing to resist, so space there can stretch more freely. The expansion rate inside a giant void could be a bit faster than the average. Like the ground itself is stretching quicker in that one spot, which raises a question. What if we're inside one, a local void, a Hubble bubble? If we are, then all our nearby measurements using supernova in nearby galaxies would be picking up that faster local rate. And the measurements of the whole universe, like from the cosmic microwave background, would show the slower, true average that could create the tension. Not new physics, just a mistake of perspective. We'd be confusing our neighborhood for the whole cosmos, so they've tested this, looking at thousands of supernova, sorting them by where they are voids or clusters. Do they see different expansion rates? The answer is maybe a little. Some studies find tiny differences, 1% or 2%, but the actual discrepancy we see is about twice that. And the cosmic microwave background puts a hard limit on the idea. For a void to explain the full tension, it would have to be monstrous. Hundreds of millions of light years wide. The early universe was very smooth. A void that big today would have left a cold spot in that ancient light. A mark we don't see. So the Hubble bubble idea is mostly ruled out, but it shows something important. The universe isn't smooth, it's lumpy, mountains of matter. Caverns of nothing. When we measure the expansion, we have to ask, are we measuring the universe, or just our part of it? Averaging light from countless galaxies, that's how we smooth out the lumps to find the true signal. It's a huge task of statistics, and the voids aren't static. They change, they grow. Dark energy pushes, galaxies on the edges get pulled toward the filaments. The voids drain, they get bigger and emptier. Their growth adds in a subtle way to the overall acceleration. They're both a product of the expansion and a part of it. So the view has to get more sophisticated. To solve the acceleration puzzle, we might need more than better numbers. We might need to understand where we are in the cosmic map. The next telescopes, like the Vera C. Rubin Observatory, will map the void network in detail. They'll trace how expansion differs in the empty places versus the crowded ones. It's not just about a better average. It's about understanding the variation. The voids remind us the cosmos has texture, and our viewpoint comes from inside that texture. The mystery of acceleration, it might not just be in the physics equations. It might be in the geography, the uneven shape of space itself, a short burst of repulsive energy right at the beginning. That's the idea of early dark energy. It's not the dark energy we see now. It's a separate thing, a fleeting form, active only in the first few 100,000 years. Think of it as a guest star. A dramatic, brief appearance on the cosmic stage, and then it exits. Its role was to give the infant universe an extra push. A temporary boost in its expansion rate, during that critical period when sound waves were traveling through the plasma. This subtle historical tweak could be the key to the Hubble tension. Our most precise ruler is the sound horizon scale. It's imprinted in the cosmic microwave background and in galaxy surveys. That scale depends on the expansion history of the universe before it became transparent. If the universe expanded a little faster during those first few 100,000 years, the sound waves would have traveled a slightly shorter distance before freezing. The standard ruler would be a bit smaller. When we use that smaller ruler to interpret the cosmic microwave background, we infer a different set of ingredients for the cosmos. And when we run the clock forward from that adjusted starting point, the predicted expansion rate for today comes out higher, closer to what we measure locally. The early boost recalibrates our cosmic yardstick. It brings the early and late universe measurements into better agreement. This early dark energy is fundamentally different from today's. Today's dark energy is weak, persistent, smooth. It acts like a constant hum in the background. Early dark energy would have been stronger, dynamic, transient. It's often modeled as a scalar field, similar to the one for cosmic inflation, but much milder and occurring later. It would have peaked in influence and then decayed away rapidly, converting its energy into the hot particles of the early universe. It was a short chapter, not the entire book. Theoretical models with this component can fit the existing data, from the cosmic microwave background and from Baryon acoustic oscillations. They don't erase the need for today's dark energy. Instead, they paint a picture of a universe with multiple phases of acceleration, an initial, violent inflation, a later, gentle early dark energy boost, a long era dominated by matter, and finally, the re-emergence of dark energy in the modern epoch. It suggests acceleration might be a recurring theme, with different drivers at different times. Yet this idea faces challenges. The timing and strength of this early boost require a delicate balance. The field must turn on and off with near-perfect precision to match observations without disrupting other well-established processes, like the formation of the first light elements. This fine-tuning makes some physicists uneasy. It can feel like adding a new element just to solve one problem, without a deeper, fundamental reason for its existence. And while early dark energy can ease the Hubble tension, it doesn't solve the vacuum catastrophe, the immense discrepancy in the predicted energy of empty space. The promise lies in testability. This isn't an untestable speculation. If early dark energy existed, it would have left subtle, specific fingerprints in the cosmic microwave background. Beyond just the sound horizon, it could affect the polarization patterns of that ancient light in detectable ways. Upcoming experiments will have the sensitivity to search for these signatures. Similarly, precise measurements of the large-scale structure of the universe could reveal the imprint of this modified early expansion on how galaxies clustered. By looking to the universe's dawn, cosmologists are following an instinct. The key to understanding the present often lies buried in the past. The mystery of why the cosmos expands at its current rate may not be solved by studying today's galaxies alone, but by deciphering the faint echoes from its first whispers of light. Early dark energy represents a bridge, a potential link between the conditions set in the first instant and the reality we measure now. It turns the Hubble tension from a contradiction into a guidepost, pointing toward a more dynamic and complex story of how our universe grew up. Dark energy, the value we measure. It's positive but just barely, a whisper. A tiny nudge. That specific, minuscule number is why you're here. If it were even a little larger, the story would be over before it began. In the early universe, matter was trying to clump together under gravity. It was a race against expansion, Dark energy acts as a counterforce, smoothing things out. If its repulsive power had been stronger by just a few dozen orders of magnitude, it would have won that race instantly. Those initial seeds of galaxies would have been diluted away before they could grow. No stars, no planets, no observers. The universe would be a vast, empty, accelerating void. And if dark energy were a large negative value, the universe would have collapsed back on itself long ago. A big crunch. Again, no time for life, so we exist in this narrow window, where the repulsive force is strong enough to eventually accelerate the cosmos, but weak enough to allow for 13.8 billion years of structure to form first. That apparent perfect balance is what we call fine-tuning, and it's not just dark energy. Several fundamental constants, the strength of gravity, the mass of the electron, they seem precisely set to allow for complex chemistry for conscious life. The odds feel staggeringly against it. This coincidence demands an explanation. One answer is the Anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. We shouldn't be surprised to find ourselves in a universe capable of producing us. It seems circular, almost trivial. But when you combine it with the idea of a multiverse, it changes. It becomes a statistical argument. If there are countless universes, a vast cosmic landscape where the laws of physics and the values of constants are randomly drawn, then it becomes inevitable that some will, by pure chance, land in that habitable window. We, of course, find ourselves in one of those rare, life-permitting universes. Our existence selects the reality we see. For proponents, this dissolves the mystery. It turns fine-tuning into a matter of probability in an unimaginably vast ensemble. Asking why our constants have their values is like a lottery winner asking why they hold the winning ticket. In a vast multiverse, every possible ticket gets drawn somewhere. The winner always wonders at their luck, but the luck itself is a guaranteed outcome. Critics, though, see this as a philosophical retreat. They argue it halts scientific inquiry. Instead of seeking a deeper, physical reason for the value of dark energy, a beautiful equation that predicts it, the Anthropic principle says there may be no such reason. It could just be a random roll of the dice. This, they say, risks making cosmology untestable. If we explain every puzzling observation by saying it had to be that way for us to exist, have we explained anything at all? The debate is fierce. Is the Anthropic principle a necessary framework, or is it a surrender of the quest for fundamental causes? Regardless, it adds a layer of meaning to the mystery of acceleration. Our existence is not separate from the cosmos's expansion. It's a direct consequence of its specific, gentle pace. The fact that we are here to ponder the dark energy that shapes our fate means its value is not arbitrary. It's a prerequisite for the question itself. This intertwining of observer and cosmos challenges our notion of explanation. Perhaps some features of our universe are not dictated by a single, elegant theory, but are instead environmental. Local bylaws in one bubble among infinite others. That doesn't make the search for a mechanism less important, but it reframes it. We're not just mapping our universe. We're discovering our address within a reality of staggering, and perhaps infinite, variety. The enigma of why expansion is as it is becomes deeply personal. The answer, if it involves a multiverse, tells us our universe is special only to us. A cherished home in an endless, mostly inhospitable, cosmic expanse. The puzzle of cosmic acceleration doesn't stay inside one field. It pushes into others. It forces a conversation across the whole scientific landscape. This isn't just astronomy's problem now. To solve it, you need particle physics. You need quantum gravity. You need computer science and statistics. The search has become deeply interdisciplinary. Take the vacuum catastrophe. That huge mismatch between predicted vacuum energy and what we observe. Our current computers can't handle the infinite sums from quantum field theory to actually calculate it. But theorists think quantum computers might one day, simulating the quantum foam of empty space on a quantum system. You could see if a stable, tiny energy comes out of the math naturally. It's a distant hope, but it shows how a tool from one area might unlock a mystery somewhere else. The collaboration is more immediate right now. Look at the data coming from projects like the Vera C. Rubin Observatory. It will image billions of celestial objects. No human team could ever sift through it. So cosmologists work with computer scientists. They build machine learning algorithms. These algorithms are trained to spot the subtle distortions of weak gravitational lensing in galaxy shapes, or to classify supernova automatically. They find patterns in the noise that human eyes would miss. This partnership turns raw data into a precise map. A map of dark matter's influence and dark energy's push. It refines our measurements to an unprecedented level. Theoretical cross-pollination is just as vital. String theorists work on a unified theory of all forces. They explore landscapes of possible universes. Their math provides a potential home for the multiverse concept. It offers a framework where the value of dark energy could be an accident of environment, not a fundamental law. It's still speculative, but this dialogue forces cosmologists to ask sharper questions about what's actually testable. Then there are ideas from condensed matter physics. The study of phases in materials. They inspire analog models of spacetime. Scientists create controlled lab systems, like ultra-cold atoms in Bose-Einstein condensates. Systems that can mimic the expansion of space or the creation of particles in a quantum field. These tabletop universes let you run experiments on cosmic phenomena, testing ideas in a way you never could just by looking at the sky. Even information theory gets involved. It was born from communication and computation. Some researchers apply its principles to the universe itself, asking if cosmic evolution follows rules of maximizing information or complexity. Could the acceleration be a feature of that process? It's a radically different lens. It challenges assumptions. It sparks new lines of inquiry. Weaving these disciplines together does more than provide new tools. It provides new ways of thinking. A particle physicist approaches fine-tuning differently than an astronomer. A computer scientist sees data patterns a cosmologist might overlook. When these perspectives collide, stubborn problems get examined from fresh angles. A problem like the Hubble tension. Maybe the tension isn't about dark energy. Maybe it's a subtle bias in how we interpret the data. A bias a statistician's model could uncover. Or maybe the solution is a particle yet to be discovered in a collider. A particle whose properties an astrophysicist can then trace through cosmic history. The journey to understand why the universe accelerates isn't a solitary path up one mountain anymore. It's a convergence of many trails from different territories of knowledge. Each field brings its own map, its own compass. By walking together, comparing notes, sharing tools, you build a much more complete picture of the terrain. The greatest breakthroughs often happen not at the center of a discipline, but at its fuzzy, overlapping edges, where a concept from one world suddenly illuminates a problem in another. This collaborative effort reminds you that the cosmos doesn't respect the academic boundaries we draw. To understand its deepest behavior, you have to be willing to think without them. This cosmic puzzle goes beyond the observatory. It touches something ancient in us, a need to know where we came from, where we're going. For thousands of years, we've looked to the stars for stories, for meaning, for our place. And now, the mystery of cosmic acceleration is a new part of that. It's not just asking how the heavens move, it's asking why the stage itself is stretching. And that question resonates. It inspires artists to visualize an accelerating void, philosophers to think about time and eternity, educators to build planetarium shows that make dark energy feel real. When a discovery challenges our understanding of reality, it doesn't stay in a lab. It ripples through culture. That public fascination is a powerful engine. It fuels support for the big telescopes and the space missions that push the search forward. But more directly, it opens doors for everyone to participate. Citizen science projects, where volunteers classify galaxies from telescope images online, turn abstract data into a shared human project. You don't need a PhD to help map the cosmos. These initiatives connect people to the quest. They turn passive wonder into active engagement. They show that science is a process of collective curiosity. The cultural impact is deep. Major cosmological shifts reshape our worldview. Learning the Earth orbits the Sun changed our sense of centrality. The discovery of an accelerating universe expands our sense of cosmic destiny. It influences how we think about time, about change, about legacy on the grandest scale. And this isn't just abstract. The drive to understand gravity and space-time gave us the precise clocks and corrections we need for GPS. A technology woven into daily life now. The relentless pursuit of dark energy, a mystery rooted in the energy of empty space, could one day spark insights into physics. Insights that reshape our concept of energy itself. In the end, this mystery is a vital gateway. It draws young minds into science and technology and engineering and math. Not with dry equations, but with a breathtaking story. A story of something unknown governing nearly everything. It fosters critical thinking by showing how even our best models are provisional. Always open to revision with new evidence. By engaging with this expanding frontier, we cultivate a society that values exploration, that supports the long, patient work of discovery. The question of why the universe accelerates reminds us that the impulse to look up and ask why is a defining human trait. In pursuing this shared mystery, we are united by wonder. Driven by the hope that in understanding the cosmos, we better understand our own extraordinary moment within it. We started with galaxies moving away from us. That was the first thing, and then we realized it wasn't just expanding, the expansion was speeding up. That fact, the acceleration, it changes everything. It's like a light, showing us where our knowledge ends. From Hubble's work to the supernova data, each step took us further out. We've mapped something called dark energy, a kind of pressure in space itself. We've hit this problem, the Hubble tension, where the numbers don't line up. We've thought about other explanations. Changing fields or gravity working differently. Even the idea of a multiverse. This isn't a small problem. It's a challenge to physics itself. It connects the smallest things to the largest. The quantum vacuum to the fate of all galaxies. It forces our theory of the small to talk to our theory of the large, and right now, that conversation isn't working. Science isn't a finished book. It's the act of asking. The universe asked us a question with this acceleration. We're still figuring out how to ask it back. That process, it drives things, it builds new telescopes. It creates teams of astronomers and particle physicists and data scientists. It pulls in public curiosity. This isn't just academic, it's about context. Understanding why the cosmos does this means understanding where we are in it. We don't have the answers. Dark energy is just a name for what we don't know. The tension in the data is a pointer to new physics, but that's the point, to be at the edge, to look into the dark. The drive isn't certainty, it's curiosity. This mystery is a gift. It means the universe is stranger and bigger than we think. The story isn't over, it's being written now. In supernova light, in labs, in anyone who looks up and wonders why.